Hello everyone, welcome back to my channel. I hope you all are doing good. Most of you would be anxious about JEE and NEET, which is getting postponed again and again due to COVID-19. I would suggest all the students to just have patience because all the frustration and anxiousness that you have can seriously harm your preparations. So keep on polishing your weak points and just be confident so that you are exam ready whenever the exams happen. So till now, we have covered IUPAC nomenclature, isomerism, both structural as well as stereo, and general organic chemistry. So, and today we are going to start organic reaction mechanism. So before starting ORM, that is organic reaction mechanisms, I highly suggest you all to just have a basic understanding of GOC very properly because that is a foundation for any organic reaction. So I will link all the playlists in the description box. If you want, you can go and have a look. Moving on to today's video, we'll be starting ORM, and in this video, we'll be having a brief introduction about what this topic is, and we'll also start reaction intermediates, starting off with carbocations. So if we look at any general organic reaction, we find there's a substrate, there's a reagent, which combine to form products. So what is a reagent? Reagent is the attacking species which attack on the substrate. So substrate is the species which is getting attacked. And in the process, we find an intermediate is formed, which is a short-lived species. Not every reaction has an intermediate, but most of them have it. And substrate and reagent combine to form multiple products or a single product. So these are the following content that we'll be covering in this topic. So it's going to be a very long playlist. So maybe around 25 plus lectures. So first of all, we'll look at intermediates, how they are formed, how their stability is determined, etc. etc. In this, we'll study about carbocations, carbanions, free radicals, carbenes, nitrines, benzines. Then we'll move on to solvents. So whenever we look at any reaction, any organic reaction, it doesn't happen in the air always. So we need a medium, right? So in this section, we'll study about different types of solvents, that is polar and non-polar. In polar, we'll be discussing about polar protic and polar aprotic and their role in the nucleophilicity. I mean, how do they operate? How nucleophiles operate in different mediums. We'll look into this, and then we'll move towards reagents. So in reagents, we'll look into nucleophiles, nucleophilicity, and electrophiles. In this section, we'll study about the basic differences between nucleophiles and bases. What is the difference between nucleophilicity and basicity? The kinetic and thermodynamic aspects also. Then we'll look into the types of reactions. So generally speaking, there are only three types of reactions, that is substitution, addition, and elimination. In substitution, we can see there is nucleophilic substitution. You can see SN1, SN2, SNNGP. Then there is electrophilic substitution of aromatic compounds, where an electrophile is getting substituted. Then if we move towards addition, we find nucleophilic addition to carbonyl compounds, electrophilic addition to unsaturated compounds, that alkenes and alkynes. And if we move into elimination, we find the elimination of alkyl halides, elimination of water. First, we'll be looking into intermediates. So what are intermediates? They are short-lived, highly energetic, and highly reactive species. And they are formed during bond cleavage. So bond cleavage can be of two types, homolytic as well as heterolytic. So homolytic means equal distribution of electrons. So let's suppose in this given example, say we are given xy. So there are two electrons between x and y. So if we talk about homolytic bond fission, these bonds will be distributed equally. Like x will have one electron and y will have one electron. And they'll have like this radicals, x plus y. If we look into heterolytic, it purely depends upon the difference in electronegativity. If we suppose the electronegativity of X is greater than Y, then the bond will shift towards X, will get X minus plus Y plus. Okay, and if it's reverse, then we'll be getting Y minus and X plus. It's simple, right? So we'll look into very details about different intermediates and how they are formed in the upcoming sections. So there are only two types of reaction in this universe, right? One can be single type reaction or elementary reaction, which can occur in a single step. Okay, so let's suppose an example. A plus B goes to product, right? If we say this is an elementary reaction, we do not find any intermediate in any elementary reaction. What we find is a transition state. What is a transition state? So what happens in a transition state, like A and B are combining to form a product, right? So a transition state is such a species in which bonds are getting broken as well as formed simultaneously. Okay, so there are partial bonds in a transition state. So these transition states cannot be isolated in any lab under any given condition. Okay, if we look at this energy profile diagram, we can say this is our reactant, this is product, and what we find over here is a transition state. Okay, we do not find any intermediate in elementary reaction. Generally, most reactions are not single step, they are multi-step reactions. Okay, like if I give an example of a single step reaction, SN2 reaction are single step reaction, E2 reactions are single step reactions. Okay, and we do not find any intermediate in SN2 and E2 reactions. Next up, we have multi-step reaction. So if we take an example for this, say A plus B combine to form, say, X star. Okay, this is our first step. Then this X star decomposes to product. This is our second step. So this X star is our intermediate, which is getting converted to product in later stages. And if you look at the energy profile diagram, we can see we have reactants, products, and here is our intermediate. Okay, here we have two transition states, TS1 and TS2. One is from the first step, TS1, and then TS2. Usually, the step in which the intermediate is formed, that is the first step in this case, is the rate determining step or the slowest step. We'll study about this in chemical kinetics, very detailed, but in this part also, like, you have to understand what is the RDS. So the step in which the intermediate is formed is called the rate determining step or the RDS. Okay, and that is the slowest step of the reaction. Some common intermediates that we are going to study are carbocations. We'll study about carbanions, carbon free radicals, carbenes, nitrines, and benzynes. We'll study about these intermediates. Starting off with carbocations. So what is a carbocation? As we can see, it's a combination of two words, carbon and cation. So a positively charged carbon atom is called a carbocation. Pretty simple. So what are the features of any carbocation? First of all, it is electron deficient because it has 6 electrons in its outermost shell. For example, if we look at this methyl carbocation or methenium cation, so if we draw the Lewis dot structure, we can see that there are 6 electrons in this outermost shell. So that is, the octet is incomplete. So we can say it is electron deficient. It is a Lewis acid because it has vacant orbitals, because you can donate 2 electrons to maintain its stability. So it is a Lewis acid. If we look at hybridization, it can have 2 hybridizations, sp2 and sp. Here we have a vacant p orbital, which is perpendicular to the plane in which this sp2 hybridized molecule is. And here we have a vacant p orbital. If we talk about the shape, sp2 has trigonal planar, and sp has linear shape. Coming to magnetic properties, as we do not have any unpaired electrons in carbocations, so it is diamagnetic in nature. Talking about rearrangements, rearrangement is possible in carbocations. It is one of the most important sections when we study carbocations, because usually questions are being asked from rearrangement of carbocations. And one more important topic is the stability of carbocations, very important. So the stability of any carbocation is directly proportional to plus I, plus M, and plus H. That is plus inductive, plus mesomeric, and plus hyperconjugation, and inversely proportional to minus I, minus M, and minus H. That is negative inductive, negative mesomeric, and negative hyperconjugation. Now we'll look at some examples to determine the stability of carbocations. First of all, in the first question we have 4 different carbocations. Here we have a 0° carbocation. Here it's primary, it's secondary, and 3°. First is methyl, then ethyl, then isopropyl, then we have tert butyl carbocation. If we have to determine the stability, we can simply say that 3° is more stable than 2, than 1, than 0, but we'll look into this. Here we have, there's no resonance in either of them. So next we'll look into hyperconjugation. Here there is no alpha H. Here we have 3 alpha hydrogens. Here we have 6 alpha hydrogens. Here we have 9 alpha hydrogens. So if there is difference in number of alpha hydrogens, there's no need to look for inductive effect, right? So we can simply say that D is more stable than C, is more stable than B, stable than A. Clear? In question number 2, we have this allylic carbocation. So here we can see this multiple bond is resonance stabilizing the carbocation. So what we find is we'll get this resonating structure. Okay, and the hybrid would be something like this. Okay. Next up, question number 3, we have some carbocations on the single skeleton, like the positions are different. So there's no resonance in either of them. Then we'll look for hyperconjugation. As you all know, we studied about this order AERHI. We'll always follow this order to determine the stability of any intermediate. First is aromaticity, then it's equivalent resonating structures, then we have resonance, then hyperconjugation, then inductive. There's no resonance in either of them. Then we'll look into hyperconjugation. Here we have only 1 alpha hydrogen, 1 alpha hydrogen. Here we have 3 alpha hydrogens over here, 2 over here, and 2 over here. 7 alpha hydrogens. Here we have 3 alpha hydrogens, and here we have 4 alpha hydrogens. So there is no need to look for inductive effect. So we can say that B is more stable than D is more stable than C is more stable than A. Clear? Question number 4, we have almost same question. There's no resonance in either of them. We'll look into hyperconjugation. We have 3 alpha hydrogens in this case, 1 and 2 and 3. Next we have 4 alpha hydrogen here, and same we have 4 alpha hydrogen here, 4 alpha hydrogens and 4 alpha hydrogens. So we can say that A is less stable than B and C both, right? But between B and C, how to determine the stability? So if we look closely into B, you can see that this CH3 is close to the carbocation, right? And it can donate more sigma electrons via inductive effect as compared to this CH3, which is pretty far from the carbocation. So as the number of alpha hydrogens is same in B and C, we can say that plus I effect is more as compared to C. So we can say that B is more stable as compared to C is more stable than A. A has less number of alpha hydrogens, and we know that hyperconjugation is the dominant factor when it comes to inductive effect. In question number 5, we have a mix of carbocations. Some have resonance, some do not have resonance, some have extended resonance. Let's have a look. In option A, we do not have any resonance, so no R effect, no resonance. Okay. In B, we have resonance. We have resonance. In C, we do have resonance and extended resonance. We have extended or more number of resonating structures. We can see like this. And in D, we do not have no resonance. Now we can say that B and C both are more stable as compared to A and D. So we can tentatively say that B and C both are more stable than A and D, but it doesn't solve our question, right? You may solve the question using this hint, right? There may be some option in which you can get the solution, but if we look closely between B and C, the one having more resonance will be more stable. So between B and C, we'll say C is more stable than B. And between A and D, we'll look into number of resonating structures. Sorry, number of alpha hydrogens. In A, we have only one alpha hydrogen, and in D, we have 4 alpha hydrogens. That means in D is more stable than A. So here is our answer. In question number 6, we have a mix of linear as well as cross conjugation. So we know from GOC that linear conjugation is more stable than cross conjugation when the number of pi bonds are similar. So here we have 2 pi bonds in both of them. So we can say that this is linear conjugation and this is cross conjugation. So when the number of pi bonds are similar, we always have linear conjugation as more stable as compared to cross conjugation. We have learned about this in GOC. Linear, we can say B is more stable than A. But it doesn't mean that cross conjugation is unstable in any means. It's just a relative thing. When we are comparing these two, B is more stable than A. It doesn't mean that A would always be very, very unstable than any other compound. Say if we compare any compound having a carbocation which is stabilized by only inductive effect, then we always have the preference that resonance is more dominant as compared to inductive effect. So in that case, cross conjugation would be more stable as compared to any other resonance, right? It's just that when we're comparing linear to cross, then we say yes, linear is more stable. That's it. In question number 7, we have this question in which we have resonance from the multiple bond in both of them. That is a tie. So we do have to look for other options. Then we have plus M effect from OH as well as NH2. Okay. And if you draw the resonating structure of both of them, you'll find that oxygen has a plus charge in A and nitrogen has a plus charge in B. I'll just give you an example. If I draw the resonating structure of A, I'll be getting this. Okay. So oxygen has a plus charge. Similarly, nitrogen will also have a plus charge when you draw the resonating structure of B. So when we compare the stability of a compound having a positive charge on oxygen and nitrogen, always nitrogen would be more stable because it is less electronegative as compared to oxygen. So we can say that B is more stable as compared to A. Fine. Next, in question number 8, we have a mix of allylic and vinylic, and allylic also like different degrees, primary, secondary, and tertiary. So first one, we are given vinylic carbocation. It is very unstable just because the carbocation is present on an sp carbon. This is an sp carbon, so it is very unstable. Fine. If we compare B, C, and D, we can see that all of them are allylic. This is primary, secondary, and tertiary. How do we determine the degree of this allylic carbocation? So always look at this carbon atom. The number of carbon atoms attached to that carbon atom is the degree of this allylic system. So here we have one carbon attached, that's why it is primary. Here we have two carbons attached, that's why it is secondary. Here we have three carbon attached, that's why it is tertiary. Okay, in all of them we have resonance. We can see it is resonance stabilized, all of them. And additionally, we have 3 alpha hydrogens and 6 alpha hydrogens in C and D respectively. Here we have 0 alpha hydrogens. You must be wondering why there is 3 alpha hydrogen and 6 alpha hydrogens in C and D, right? So just to make it clear, if you draw the resonating structure of B, say for example, if I draw the resonating structure, I'll be getting this, right? Just look at this resonating structure. Here you can find there is 3 alpha hydrogen, right? So you have to calculate the number of alpha hydrogens in all of the resonating structures. Similarly, you can find there are 6 alpha hydrogens in option number D. Comparing all of them, we can say that D is more stable, then C, then B, then we have the vinylic system. Fine. Moving on, in question number 9, we have this benzylic primary. Here we have secondary benzylic, tertiary benzylic, and this is non-benzylic, a normal system. Now if we compare, all of them have resonance, right? There's a resonance from the ring A, B, and C, not the D. If we compare A, B, and C and D, D would be the least stable because there's no resonance. Fine. So we can say that A, B, and C, all of them are more stable than D. And while comparing A, B, and C, you have to look at the number of alpha hydrogens. There's 3 alpha hydrogens and there is 6 alpha hydrogens. That's pretty simple. So we'll say C is greater than B, greater than A, greater than D. Next up, we have question number 10, in which at para position to the carbocation, we have different groups, and we have to determine the stability of these following carbocations. So we know at para position, we can observe resonance as well as hyperconjugation, and both of them are not distance dependent. Inductive effect is distance dependent and decreases with increase in distance. OH will observe plus M effect. CS3 will show hyperconjugation with 3 alpha hydrogens. Cl will show minus I effect. NO2 will show minus M effect. We know for all the halogens, the inductive effect is dominant over its mesomeric effect due to their high electronegative nature. Now if we compare, we have seen that the carbocation is stabilized by electron donating groups and unstable by electron withdrawing groups. So the most electron donating group is OH, that is donating by resonance. So we can say A is most stable. Then we have electron donating as hyperconjugation by B. Then we have two electron withdrawing groups, and the most electron withdrawing group is NO2, that is by -M. So we'll say C, then D. Fine. Question number 11. Here it's given similar question, but the groups are present at meta position, and we know that at meta position there's no resonance, there's no hyperconjugation. The only electronic effect that we observe is the inductive effect, right? So OH will show -I effect, CS3 will show +I effect, NO2 will show -I effect. Now, in order to determine the stability order, we have to understand which one is more -I, OH or NO2, because we know B is most stable because of electron donating nature. Between A and C, we can see that NO2 will have strong -I because it has strong -M also, right? Because of the two O groups, if you look at the structure, because of these two O groups, it is highly electron withdrawing group, one of the highest electron withdrawing group in all the series of -I that we have studied in GOC. So we can say B is most stable, then we have A, then we have C. Clear? Question number 10, we have a mix of aromatic and anti-aromatic compounds. We have studied aromatic and anti-aromatic compound. So A is an anti-aromatic compound. Anti-aromatic compound. Because the conditions are, it should be planar, cyclic, closed loop of resonance, and 4n pi electrons. B and C are aromatic because the conditions are, it should be planar, cyclic, closed loop of resonance, and 4n plus 2 pi electrons. Then we can say aromatic compounds are very, very stable as compared to anti-aromatic compounds. Therefore, B and C are more stable than A. But between B and C, to determine the stability, we have to look at the number of pi bonds. Whenever you compare two aromatic compounds, you should always look at the number of pi bonds present. So in C, we have 6 pi electrons, in B, we have 2 pi electrons. So the 6 pi electron system would be more stable as compared to 2 pi electron system. So we'll give the answer as C, then B, then A. Next up, we have this question in which the positive charge is stabilized by resonance as well as hyperconjugation. In A, we can see the nitrogen is showing +M and resonance stabilized. So here it's +M. In B and C, there's no resonance. So A would be more stable than B and C, right? But when you're comparing B and C, how do you determine the stability? There's no resonance. We'll look into hyperconjugation. There's 4 alpha hydrogens and 4 alpha hydrogens in both of them, right? 2 of them over here, 2 over here, 2 over here, and 2 over here. Now, if we have to compare the stability of these two carbocations, then we have to look at the inductive effect. In B, the nitrogen atom, this nitrogen atom being the more electronegative atom in the entire ring, can withdraw the electrons more as compared to C. So here the -I effect would be very high as compared to C. This is because the distance between the carbocation and the nitrogen atom is very small in B as compared to C. In C, we have the carbocation very far from the electronegative atom, which makes it more stable than B. So we can say that A is the most stable because of resonance. Then we have C, then we have B. Pretty simple. Next up, we have this question. In this question, we can see that the number of alpha hydrogens in A is 3 alpha hydrogen, and in B we have 2 alpha hydrogen. Theoretically speaking, the stability order would be A greater than B, right? Because we don't have resonance in either of them. And looking to hyperconjugation, we can say A is greater than B, but it is incorrect. It is incorrect. The actual answer is B is greater than A. Because if you look closely into A, you can find that this carbocation is surrounded by highly electronegative atoms which can withdraw electrons by -I, which can make it very, very unstable. Whereas in B, the distance increases from the electron withdrawing groups, which makes it relatively more stable as compared to A. Even though there is difference of 1 alpha hydrogen, still the inductive effect is dominant in this case, so it violates the AERHI order. So it is just like an exception, but a reasonable exception. Like you can justify this statement because these 3 Cl groups would pull more electrons in A as compared to B, right? So moving on, in question number 15, we have a mix of inductive as well as hyperconjugation, combining some bond energy concept. So in B, A and B, we can see we have hyperconjugation. We have 3 alpha hydrogen in A, we have 3 alpha deuterium in B, right? We do not have any hyperconjugation in C as well as D. So we can say A and B are more stable as compared to C and D, right? But while comparing A and B and C and D, we have to look into some factors. While comparing A and B, we'll have to look into the bond energy concept. Bond energy. We know the bond energy of CH is less than CD. When we studied hyperconjugation, we saw this concept, right? CH bond energy is less than CD, just because of extended overlapping of D with the carbon atom. Now, when we are doing this hyperconjugation thing, the less bond energy of CH would facilitate more stability towards the carbocation, right? So CH bond would break more easily, which will stabilize the carbocation more as compared to CD, which has a higher bond energy. Therefore, we can say that A is more stable than B due to less bond energy of CH. When we are comparing C and D, we know, let's make this structure CH, H, and H plus charge. And similarly, we have D, D, and D. Now we can see that the hydrogen is donating some sort of electron to the carbon atom. And similarly, deuterium will also donate some electron to the carbon atom to stabilize the carbocation. But when we are comparing hydrogen and deuterium, we all know that the electronegativity of a heavier isotope is always less as compared to the lighter isotope. So the electronegativity of deuterium is less than hydrogen. That means deuterium would be donating more electrons towards the carbocation as compared to hydrogen. So which solves the question, right? Then we can say that D is more stable than C, because hydrogen would donate less electron because of its higher electronegativity, which would destabilize the carbocation. Next up, we have some groups present at para position. Here we are given CS3, which can show hyperconjugation with 3 alpha hydrogen. Here we are given 1 alpha hydrogen hyperconjugation. Here there is no hyperconjugation. Still, we can show that the plus I effect is different in all of them. Here it's the highest, it's low in the intermediate stages, and here it's very, very low, right? But we know the inductive effect is distance dependent. As you increase the distance, the effect diminishes. So inductive effect will never be a factor in determining the stability in this case, because After 3 carbon atoms, it is almost negligible. Here it's almost 4 and 5 carbon atoms. So we'll only be looking into the hyperconjugation concept. So looking into hyperconjugation, we can clearly state that A would be more stable than B, then C. Fine. That's all for today's video. In the next video, we'll be looking into some special cases of stability of carbocations, that is cyclopropyl methyl carbocation, and some more examples and a general stability order of all the carbocations. We'll also look into the formation of carbocations, how they are formed in different reactions. If you find this video helpful, please like, share, and subscribe to the channel for more videos. And if you have any doubts, you can put them in the comment box. Thank you so much for watching. See you in the next one.